Welcome to another video from McFatter Tech Musser. If you like these videos, please click subscribe. Alright, so today we're going to be doing a lab from Wireshark on TCP. You also have a lab on UDP. What's the difference? Who can tell me the difference between TCP and UDP? Right, handshakes, no handshake, just send the data. I'm not concerned whether or not it got there. That's UDP. So if I'm downloading an email, UDP or TCP? TCP. Why? Because I have to ensure that I've gotten every packet to reassemble that email. If I'm getting a web page, UDP or TCP? TCP, because I need to make sure that I've gotten all the components of that web page to be able to reassemble it. Perfect. So that's what we're going to be working on today. So let's go ahead and we're going to jump into the quiz. And as you can see, we're going to be using the TCP-Wireshark-trace 1.1 file. So I'm going to go ahead and grab that, get that opened up. So as we can see, we've only got two trace files that we've got to work with. We're using 1-1. And we can immediately see we've got some information here on our screen. Let's take a look at what the requirements for our quiz say. They're going to tell us we want to filter by HTTP. So we're going to do a display filter up top, HTTP. We're left with two packets. A GET request, hey, I want a web page. And a 200 OK, here's your web page coming back from the web server. We're going to expand IPv4, TCP, and HTTP. So that first packet is selected. In fact, I'm going to raise that up there so I got a nice big view. I'm going to expand HTTP, TCP, IPv4. We're going to do our edit copy all visible items and or Control-Alt-Shift-A shortcut and paste our evidence into our first box. So highlighted, Control-Alt-Shift-A, jump back over. We paste our evidence to support our conclusions. You come to me, you tell me we got a problem, you got to do this. I say why. This is our why. This is what's occurring. So we can see some information here. If we look here, we've got a GET request, and it's just not one little packet. It's reassembling a whole bunch of different packets. We're going to be looking at this. That's TCP, right? So our first question says, hey, what's the IP address of the client computer, the source IP address? What's our source IP address? Yeah, pretty evident right there. It's on our screen because we did our filtering, we did our columns and display. So we've got it right there, 192.168.86.68. That was easy enough. What port number is our client side? 55639. Okay, thank you. That's not HTTP. We're trying to get a web page. Why is it this big port number? And the client's not the one running the web server. That's a dynamically generated port number. It's simply a dynamic number. It says, hey, when that request comes back, return it here. The web server is the one that has port 80 running in this case because we're doing clear text HTTP. So, in addition, what's the IP address of the web server? What's the port that the web server is running? Kyle? Yeah, what's the IP address? 128.119.245.12, right. And Oscar, what's that port number that it's running on? 80, because that's HTTP, right? Common, well-known port number. Now, looking at our TCP SYN, before we can request that web page, we have to do a TCP three-way handshake and establish a communication to that web server. So take a look here. The question is, what is the sequence number of the TCP SYN segment that's used to initiate the TCP connection between the client computer and the web server? Make a note, this is the raw sequence number in the TCP segment itself, not the packet number. Remember, Wireshark just assigns that, as a sequence number. That's not what we're looking for. Yes. Which number? Right here? Well, oh, wait a minute. I got something wrong here. There. Let's take a look at something. So, remember they're asking, is this a TCP SYN segment? This is the start of our HTTP communication. This is after the three-way handshake is done. They're asking for a TCP SYN.
Yeah, this is the acknowledge, right?
The TCP SYN is the first of the three-way handshake. What we're looking at here, by filtering by HTTP, that's the actual communication of the exchange. Hey, I want this web page. Give me the web page. This is not the TCP three-way handshake that begins with the TCP SYN. So if I want to see that communication, should I change my display filter?
Yes.
I'm going to change my display filter to TCP. Now remember, our GET request is packet 153. I'm going to hit enter. We see a lot more packets now, right? Take a look here. There's a lot of stuff going on here. These are all acknowledgments. Look right here. TCP SYN, SYNACK, ACK. Here's that TCP SYN that we're looking for. In fact, that's the very first SYN synchronization request that we saw in there. Until we get all way past, I mean, that's the entire conversation. There's only one SYN. So with that in mind, so that's our packet number 1, correct? So now, Kyle, what is the sequence number that you see? The raw sequence number.
423.66849.20.
Right, because this is the start of establishing the link to be able to do that communication. This is me saying, Kyle, want to have a conversation. Are you ready? And you respond back with the SYNACK saying, yeah, I'm good. I'm ready. Are you ready to go? And then I finally acknowledge and say, yes, I acknowledge that you're ready to start our communication. I am as well. And now the three-way handshake is completed, and we're ready to request, either be it an email, be it a web page, whatever it might be. So, right there, that's our raw sequence number. Four two three 664-9187. So, after all that, what is it in this TCP segment that identifies this segment as a SYN segment? What in the segment identifies it as a SYN segment? Take a look. Let's look in our TCP section. What identifies this as being a SYN segment? It has nothing to do with ports, none of the raw numbers. Yes, Kyle?
The first segment of the TCP connection.
It is, but what identifies that as being the SYN segment?
There's a flag set.
Bingo. See flags? And what do we see set in that flag? We see a bit turned on. So your answer is the SYN bit is set to 1, and that says, hey, this is identified as being a SYN TCP segment, a SYN request. So right here, the SYN bit is set to 1 in the flag field. That identifies it. In fact, if you look back there, you can see all the different things. So if this was the next segment, the SYNACK, what bits do you think are turned on? Exactly, the ACK and the SYN. Having the bit turned on, it's the same as that power switch, on off, right? It identifies, hey, this is active, this is not. So our next question, like I said, these labs get a little bit more difficult, right? So our next question is, will the TCP receiver in this session be able to use what's called selective acknowledgments? Now, remember, we don't have the textbook. I didn't make you buy this textbook. We're not attending the course that uses this textbook, but we're using the labs out of the textbook. So here again, this may not be an answer that we haven't read about, so we may not know. So if we look here, it says, will the TCP receiver in this session be able to use selective acknowledgments? Well, the answer is yes.
That's under the options column, right?
It is under the options. In fact, if you expand options, wasn't it in here? No operation, end of options. The SACK. Where's the SACK? Right there. SACK permitted. That's your selective acknowledgments. SACK, selective acknowledgement. So the answer is yes. The TCP options field in this SYN segment indicates that SACK can be used. We may not understand all the different things that are going on in these headers, but it's all there. All the information's there. Now moving on to the SYNACK. What is the sequence number? Remember that now this is the raw sequence number. What's the raw sequence number for the SYNACK? Oscar? Absolutely. Absolutely. It's all right there. Now, building on what we just learned about the SYN packet, what in this segment identifies the segment as a SYNACK segment? John? They're both set to 1. We can see that right here. Acknowledgement and SYN. They're both set to 1. Now our next question. What is the value in the acknowledgement field of the TCP SYNACK segment that's used to initiate the TCP connection between the client computer and the web server? This is the raw value carried in the ACK number field within the segment, not the relative ACK number. What is the value in the acknowledgement field? $91.88, yes. That number sound familiar? It's one step up. It's one sequence higher than our ACK. The ACK ended with 91.87. Right there. 423-664-9188. That's the acknowledgement of that SYN. So, with what I just said, how did the web server determine the value used in the acknowledgement field number? The value of the ACK number field is the sequence number of the next expected byte of data to be received at the server on the client-to-server direction of this connection. One higher than the sequence number used as the sequence number of the initial SYN segment. It's simply incremented by 1. Now, another raw sequence number. The first segment containing payload data. What is the sequence number of the TCP segment containing the HTTP post command? To find the post command, you need to dig into the packet content field at the bottom of the Wireshark window. Now, it used to be at the bottom, now it's at the side. So we gotta move this back over so we can see. In fact, we'll make the whole window a little bit wider. We're looking for a post command. Well, yeah, where did we do the post? Right there's your post, right? In fact, if you look, but the question is, do you see the post command in here? You see it up here in the info. But we don't see it. All we see is the text. This is the reply back, right? This is the request. See the post command? Read the note. Think carefully about this question, as the obvious answer may not be correct. So we're looking for the TCP segment that contains the ASCII2 string post in the data payload. If you only look at HTTP, you're going to see that info talking about HTTP post message. That's actually the very last segment. Remember, this is a page that's being requested that contains multiple packets to reassemble that web page. The HTTP post message that you see in the info is actually the very last segment. We're looking for the post in the data payload. Packet, Wireshark identifies it at packet number 4. You can see that right here. Right there's the post. And that's in your TCP data segment. So the question is, what's the raw sequence number?
423.664.9188.
The same sequence number that we saw as the acknowledgement in the SYNACK, right? Our next question is, how many bytes of data are contained in the payload data field of this segment? How many bytes of data are contained in it? 1448, right there, TCP segment length. We can also see it up in the description, length 1448, 1448. The first segment containing payload data. Did all of the, now we what this is downloading a copy of Alice in Wonderland. Did all the data in the file alice.txt fit into this single segment? Remember, we said that there was multiple segments, right? So not even close, right? Not even close. The alice.txt file is much larger, and so multiple TCP segments need to be transferred. So with that in mind, what we want to do is consider the TCP segment containing the HTTP post as the first segment in the data transfer part of the TCP connection. At what time, remember this is the one that had the HTTP post in the data transfer part. What was the time that occurred? Remember, the default listing here is time from start of the capture. We've still got that packet selected, right? So what's the time value? 0.024047. Yep. Our next question states, consider the TCP segment containing the HTTP post as the first segment in the data transfer part of the communication or connection. At what time was the ACK for this one first, for this first data containing segment received from the web server? Remember, every communication has to be acknowledged. When was that acknowledged by the web server? Negative. We're looking for a response back from the web server. So how would we know which one it is, first off?
So the web server would be talking on port 80.
Correct. So remember this, you'll see that this is requesting the start of that transfer. So we're looking for the response back from the web server that begins that. Well, where's the first packet we see coming back? Packet 7. And what's the time value on it? .0.052671. So we're looking at round trip time. In other words, how long did it take? Consider the TCP segment containing the HTTP post as the first segment in the data transfer part of the connection. You've just determined when this first segment was sent to the web server, and when the acknowledgement for that segment was received from the web server. What would be our round trip time? So, in other words, what's the one ACK time versus the other ACK time? 0.028624, right? You just subtract one from the other, right? What about the second client to server segment? We were looking at the first, right? This was our post. This was our response back from the web server.
How did you know that was a post?
Because it says post right there. It says post right in the data segment. So our second is number 5, right? And the corresponding response to it is packet number 8. So do the math. So 5 and 8. I've got the answer. Anybody else? How much is the time value of 5 subtracted from the time value of 8? 0.028628. Exactly. Yeah, we're already most of the way through this. We're already two-thirds of the way done. Now, this one might be a little bit more difficult. And here again, we don't have the book, so we haven't read this. This deals with estimated round trip time, estimated RTT. So we don't have the equation from page 236 of the book, so I'm going to give you the answer. And that's another reason why we're doing this particular one together. It asks what's the estimated round trip time, and the estimated round trip time is 0.0286245 seconds. 0.286245. If we had read that, we could do that. But we didn't. Observed TCP segment lengths. We've already seen this. In fact, we already answered this. What's the length, the header plus the payload, of each of the first 4 data carrying TCP segments? Say it louder. 1448, absolutely. If you look right here, 1448, length, 1448, length, 1448. And then the next 2 are responses back from the web server, and then our next one here again, they're also 1440. You'll see 1448 continues, but they're only asking for the first 4. 1, 2, 3, and 4. 1448. Now, we have buffer space. In other words, how much data can we buffer? What's the minimum amount of available buffer space advertised to the client by the web server among these first 4 data carrying TCP segments? It says enter an integer value, and you see there's a note, note 1. Give the Wireshark reported value for window size value. Which would then be multiplied by the window scaling factor to give the actual number of buffer bytes. What is the window scaling or window size value?
131,712. Let's calculate window size. The original will be 2058.
Well, that's the actual window size, but remember they're asking
The calculated, right? The amount of available buffer space advertised.
calculated window size, window scaling factor. Here again, we haven't read all the text on these things, right? Your answer is 249.
Okay.
Just trust me. Your answer is 249. So that doesn't seem like that much available, right? For this window size for the buffer. Do you think that lack of space ever throttles the sender for these first 4 segments? Remember, now the calculated window size, see here? Look at your calculated window size and the actual window. And what's the TCP segment length?
1448.
Does it exceed any of those sizes?
2058 exceeds 1448.
Now the receiver advertised window is always larger than the amount of buffering needed. The answer is no, the receiver advertised window is always larger than the amount of buffering needed for the more than 1500 byte segments. Or I've got no idea. But that's not the correct answer. Our next question asks us, are there any retransmitted segments in the trace file? Well, it's kind of hard to tell. But if you look down through it, if you could actually track each request, each responding acknowledgement, there are no retransmissions. In fact, you would see it noted. Remember how Wireshark color codes things? There are no retransmissions.
And if there were, it'd just be a different color, right?
Yeah.
Okay.
Question 25. How did you determine that there were none? Well, we can check the sequence numbers for the segments sent. Those sequence numbers, these sequence numbers are continually increasing in numeric value. The number consistently increases. If it didn't, if there was a repeat, that's a retransmission. So that alone will tell you. If you saw a sequence number repeated, that was, hey, I didn't get this, resend it. So in looking at the sequence numbers for the segments sent by the client to the web server, we found that they're all increasing, no repeats. our question number 26 in our quiz. How much data is being ACKed? How much data does the receiver typically acknowledge in an ACK among the first 10 data carrying segments sent from the client to the web server? Exactly 1448. And we can see it right there in the length. 1448, 1448, 1448, 1448, over and over again, right? Now, I did grab one of the tables out of the text for this next question. Can you identify cases where the receiver is ACKing every other received segment among these first 10 data carrying segments? Is the web server acknowledging every other one? Or is it acknowledging each one? So our first 10. So here's our post. It acknowledges it. Here's the next one. It acknowledges it. Is it doing every other one? Or is it acknowledging each one? It's each of the first 10 ACKs acknowledge exactly 1448 bytes of payload data. Now, throughput. This is interesting. Think about this. Does anywhere in this Wireshark packet capture tell you what the throughput is? In other words, bytes transferred per unit of time, like 100 megabits per second or gigabit. Actually, we can tell.
Is it the bytes in flight value?
Well, look at the hint. How long did it take to transfer the entire file? How large was the file? Your calculation deals with bits transferred and time. So let's see. There's our post. Here's where it was received, where we finished sending it. Remember, this is us uploading a file, uploading a copy of Alice in Wonderland in text form. Here's the acknowledgement. Question is, what was the total size? And how long did it take? Right, so we completed the transfer at 0.192625 seconds. We started the transfer at, what was it, 0.024047 seconds? Or thereabouts. So subtract that from the 0.192625. Take a look at your calculated window size on that final packet. 194.816. Divide 194.816 by the time difference, which is 0.162578. And you're going to come up with this right here. So with that in mind, what's the throughput? What was it, packet 5? Where the post was at? Around 1.2 megabits per second. That was the actual transfer throughput. Here, this is how we calculate. This is how we determined it. So here's our final. Okay, we've received your transfer, and it's been reassembled. Everything came through correctly. See your window, calculated window size. That was the total size that was received. In fact, if you go back up a couple packets, you'll see that it starts to decrease in size as data, or inversely, as data is being received, it goes up in size, correct? To that final 194.816. If you go all, and that was at 0.192625 seconds. If you scroll all the way back up to where that post was at, where the post was at, and you subtract that from the final time, that gives you the amount of time it took for the transfer. If you take the total bytes that were transferred and divide it by that time, that's bytes per second.
Is that looking in that window the only way to find posts?
Yes. Because remember, this is an upload. That's why it's a post. It was not a HTTP GET request. That's us wanting to get a web page. This was us posting an upload. That's why here on packet 153 we see post. That's saying, hey, we want to upload. So 194.816 divided by 0.168578 equals 1155643, or approximately 1.2 megabits per second. And had we looked forward, we might be able to figure that out. How did you calculate it? Bytes transferred per unit of time. It took a guess. I guess the person that wrote this question would have the newest and fastest wireless, right? I just took a random guess, was able to get it right. Or I figured out how many bytes were transferred during the amount of time between when the client sent the first segment containing the first bytes of data in alice.txt and when the last segment in the connection containing the last bytes of data in alice.txt was sent. Time difference, number of bytes, division, answer. Our last couple questions, last two questions, tells us to use something different. Time sequence graph Stevens, a plotting tool, to view the sequence number versus time plots of segments being sent from the client to the web server. And it's being sent in what we call fleets of packets, around 0.025 seconds, 0.053 seconds, 0.082 seconds, and about 1/10 of a second. So let's see. It's been a while since I did this. Statistics, stream graphs. time sequence Stevens. So I'm going to select that. So statistics, TCP stream graphs, time sequence Stevens. And that doesn't really tell us much. Down here in the bottom right, click switch direction. Now we can see what's going on there. Take a look at our questions here. Which of the observations below best characterizes the congestion control aspects of this behavior? We can see throughput, a couple packets, a couple more packets, even more packets, even more. So a couple packets got transferred, a couple more. It was like in bursts and increasingly larger bursts of packets. So here again, we haven't read the text from the book. So maybe some of these terms are new to us. Congestion avoidance, whatever. But look at this. TCP's in its slow start phase. There's a fleet of 3 packets, then a fleet of 6 packets, a fleet of 12 packets, a fleet of 24 packets. Is that what we see there? That's what I see. Look at the screen. 3, then 6. Exactly what they're describing. These groups, these fleets of packets being transferred. It starts off slow with 3, and then 6, and then 12, and then 24. See it right here? There's your 3, there's your 6, there's your 12, there's your 24. It's starting off in its slow phase. And as it can burst more, it does. Now, using that same graph that we've got on our screen, we're looking at those fleets of packets at 0.025, 0.053, 0.082, and 1/10 of a second. They appear to have some periodicity. What can you say about the periods that they're appearing on? Remember the round trip times that we found the calculation to earlier? Let's see, where was that? That was back on question number 20, and our round trip time was 0.028. .028, 0.026, somewhere in there. The answer is the period roughly corresponds to the round trip time between the sender and receiver, which we computed earlier, in this case, to be around 0.026 to 2.8, or 0.028. So, roughly corresponds to the round trip time. So like I said, the reason we're doing this together is there's a lot of the concepts in here that are being reinforced from what students would learn in the textbook, that these labs were written to accompany. We don't use the textbook, so we need to have a little bit of assistance. Go ahead and submit your quiz. I'll go ahead and add the fact that you get credit for the information being submitted for your packets, for your evidence, and you'll get your final grade. Hopefully that shows you a little bit more about how TCP works. It's connection based. We have to acknowledge the receipt. Doesn't matter whether we're uploading a file or retrieving a web page, the transfer of each one of those packets gets acknowledged. If it doesn't get acknowledged, it gets retransmitted. Hope you enjoyed this lab. Like I always say, see you in the next lab or lesson. Take care, everyone.